Imagine taking the deep metallic heart of a planet and lifting it out into space, leaving it exposed to sunlight and micrometeorites for billions of years. That is the idea behind 16 Psyche, a strange, dense world in the main asteroid belt that may be the closest thing in our solar system to a naked planetary core. As we fly through the crowded plain between Mars and Jupiter, most asteroids we pass look familiar, dark carbon-rich bodies, or stony fragments of unfinished planets. And then, one object stands out. It is large by asteroid standards, roughly a couple of 100 kilometers across, with a mottled, light dark surface and hints of a metallic sheen in radar echoes. This is 16 Psyche. It does not behave like typical rock. Radio and spectral observations suggest that a significant fraction of its interior is metal, iron and nickel, mixed with silicates, making it unlike almost any other world we have ever approached. On Earth, metal like this lies far beneath our feet, locked away in the core under thousands of kilometers of rock and mantle. We infer its existence indirectly, from gravity, seismology, and magnetic fields, but we will never touch it. Psyche offers something radically different: the possibility that collisions in the early solar system stripped the outer layers from a forming protoplanet, leaving only its interior behind. If that is true, then 16 Psyche is not just another asteroid. It is a fossilized piece of planetary anatomy, a cross-section of how rocky worlds begin. This is where NASA's Psyche mission enters the story. Launched to rendezvous with this object in the main belt, the spacecraft is the first ever sent to an asteroid thought to be dominated by metal. Over the coming years it will cruise outward from Earth, using solar electric propulsion and planetary flybys to match Psyche's orbit. When it arrives, it will not land or collect samples. Instead, it will orbit this world for many months, mapping its gravity field, imaging its scarred surface in high resolution, and using spectrometers and magnetometers to read the chemical and magnetic fingerprints locked in its rocks and metals. The stakes are high. If Psyche truly is the remnant core of a once-growing planet, its structure and composition can tell us how protoplanets differentiated, how heavy elements sank inward, how lighter rocks floated above, and how violent collisions reshaped young worlds. If, instead, it turns out to be a more complex mixture of metal and rock that never reached core status, that result is just as important. It would force us to refine our models of how solid bodies accrete, fragment, and reassemble in the dusty chaos around young stars. In this episode, we will explore what makes 16 Psyche so unusual, why scientists suspect it may be a metal-rich world, and how the Psyche mission is designed to test that idea. We will see how a single asteroid can challenge our assumptions about what planets are made of, and how far we are willing to go to read the secrets written in their deepest layers. 16 Psyche is not just another rock in the main asteroid belt. It is one of the strangest and most informative objects we've found there, a body that may preserve, in exposed form, the kind of metal-rich material we usually hide deep inside fully grown planets. At the most basic level, 16 Psyche is a mid-sized asteroid, discovered in the 19th century and now known to be roughly 220 to 230 kilometers across. It is not a perfect sphere. Models built from light curve and radar data show an irregular, lumpy shape, but large enough that its own gravity has rounded the overall outline compared with smaller, jagged fragments. Psyche orbits the Sun in the main asteroid belt between Mars and Jupiter, completing one lap in just under 5 Earth years, at an average distance of about 3 astronomical units. It also spins quite rapidly, turning once on its axis in a matter of hours, so any point on its surface cycles through harsh sunlight and deep shadow in a single asteroid day. What makes Psyche truly stand out is not its size, but the way it interacts with light and radio waves. From Earth, we cannot resolve fine surface details directly, but we can probe its properties by combining radar echoes with spectroscopy. When powerful radio beams were sent from facilities like Arecibo and Goldstone and bounced off Psyche, the return signal was unusually strong compared with that from typical rocky or carbon-rich asteroids. High radar reflectivity is a hallmark of metal-rich surfaces. Solid or fragmented nickel or iron reflects radio waves far more efficiently than dark carbonaceous dust or low-density silicate rubble. At the same time, spectra taken in visible and infrared light show features consistent with silicate minerals mixed into that metallic background, rather than a pure iron or nickel surface. Together, these observations paint a picture of Psyche as a compositionally unusual body. It does not behave like the more common carbon-dominated C-type asteroids, nor like the brighter stony S-types. Instead, it falls into the rare class of M-type, metallic, asteroids with an overall density and radar signature that point to a significant fraction of metal alloyed or intergrown with rock. Some models suggest a heterogeneous world with patches richer in exposed metal and others dominated by silicate material, perhaps corresponding to ancient impact basins, mantling, or buried layers brought to the surface. Even with those complexities, Psyche remains one of the best candidates we have for a body that preserves, near the surface, the kind of material that usually sits deep inside larger differentiated worlds. This is why scientists cautiously refer to Psyche as a metal world, while stressing that the phrase is shorthand, not a literal description of a solid iron ball. Early interpretations, based on limited data, imagined something close to a stripped planetary core. More recent mass and volume estimates, plus spectral refinements, favor a more nuanced structure, a large rubble-like body whose bulk is a mixture of metallic and silicate components, perhaps the surviving interior of a once larger protoplanet that was repeatedly shattered and reassembled. If Psyche really is a fragment of a differentiated parent body's interior, it offers a unique chance to study the kind of metal-rich regions that, on Earth, lie far below our feet in the inaccessible core. If, instead, it turns out to be a complex hybrid that never fully differentiated, that result is just as important. It would reveal new pathways by which metal and rock were sorted, mixed, and reworked during the solar system's violent youth. In both scenarios, Psyche is not an oddity on the margins. It is a key witness to how solid planets begin. When planetary systems are young, they are not quiet places. They are hot, violent factories where worlds are assembled and stripped apart again. In that chaos, something like 16 Psyche could have been born, not as a simple rock, but as the exposed interior of a world that almost became a planet. At the beginning, newly formed planetary embryos are made from a mixture of metal and rock. As they grow, they heat up from several sources at once: the energy of countless impacts, the slow squeeze of self-gravity, and the decay of short-lived radioactive elements like aluminum-26. Once the interior becomes hot enough to soften or partially melt, the material starts to separate. Heavy elements such as iron and nickel begin to sink toward the center, while lighter silicate minerals rise outward. This process, called differentiation, naturally builds a layered structure, a dense metallic core, wrapped in a rocky mantle and crust. On Earth, we infer the existence of this core from its gravity, its magnetic field, and the way seismic waves travel through the planet. But we will never see it directly. It lies almost 3,000 kilometers beneath our feet. The same is true for Mars and Venus. Even Mercury, with its enormous iron core, hides that metal heart beneath a shell of rock. Everywhere we look, the cores are buried. If we want to understand what a planetary core looks like, how it cools, fractures, and records magnetic fields, we are forced to study it indirectly, through models, experiments, and the chemistry of iron meteorites. 16 Psyche offers a different possibility. Radar observations from Earth show that Psyche reflects radio waves far more strongly than typical rocky asteroids, a sign that its surface is rich in metal. At the same time, its bulk density appears too low for a solid iron sphere. It is likely a mixture of metal and silicates with significant porosity. That combination suggests an object that has undergone substantial differentiation, but not in the neat, symmetric way of a finished planet. Instead, Psyche may be a fragment from deep inside a much larger body, where metal and rock were already beginning to separate when something catastrophic intervened. In one leading scenario, Psyche started life as the core region of a protoplanet perhaps hundreds of kilometers larger than it is today. During the late stages of planet formation, that protoplanet could have suffered a series of giant impacts with other growing worlds. Each collision would have stripped away more of its outer rocky layers, chipping off mantle and crust. Over time, the surviving remnant would become increasingly metal-rich, until only a distorted, partially exposed core remained. What we now call 16 Psyche might be that remnant, a shard of planetary interior left stranded in the asteroid belt. However, nature rarely follows only one script, and there are other plausible stories. Psyche might not be a cleanly exposed core, but a body that only partially differentiated. In this picture, the original protoplanet never fully melted. Metal and silicate began to segregate but remained mixed on large scales. Later impacts could have stirred this mixture, leaving an object with patches of metal-dominated terrain and regions that are more rocky. From a distance, the integrated signal would still look metal-rich, but the interior structure would be more complex than a simple core fragment. Another alternative is that Psyche is the survivor of a violent mixing event. Imagine a collision between a metallic core fragment and a more typical rocky asteroid. The debris from that impact could reaccumulate under gravity into a new rubble pile body, containing both kinds of material in different proportions. Some areas might be dense and metal-dominated, others more porous and rocky. Over billions of years, smaller impacts, space weathering, and thermal stresses would further sculpt the surface, producing the landscape the Psyche spacecraft will actually encounter. The mission is designed to distinguish among these possibilities. By precisely tracking the spacecraft's motion around Psyche, scientists can map its gravity field and infer how mass is distributed inside. Is it centrally concentrated like a core, or more even, like a mixed rubble pile? A magnetometer will search for traces of remnant magnetization, a fossil magnetic field that could only have been imprinted if Psyche once had a molten, convecting metallic core generating a dynamo. Cameras and spectrometers will examine the surface in detail, looking for variations in composition, texture, and color that might reveal layers, impact basins, or regions where metal and silicate are segregated. If Psyche turns out to be close to a stripped core, it will be our first direct look at a planetary interior, frozen midway through the process that built the terrestrial planets. If it is instead a complex hybrid, part core fragment, part rubble pile, it will still tell us how often such violent mixing occurred, and how messy planetary assembly really was. In either case, this single asteroid becomes a laboratory for studying the deep, hidden layers of rocky worlds without having to drill through thousands of kilometers of rock. In that sense, 16 Psyche is less a curiosity and more a missing chapter in our own planet's biography. By reading its metal and stone, we are trying to reconstruct the moments when worlds were half-finished, shattered, and rebuilt, and when the cores that now lie buried at the centers of planets were briefly exposed to open space. When you send a spacecraft to a world more than 300 million kilometers away, you don't fly in a straight line. You design a journey that uses gravity, sunlight, and time itself as tools. NASA's Psyche mission is exactly that kind of journey, a long, spiraling path from the inner solar system out to a strange, metal-rich asteroid in the main belt. Psyche began its voyage in October 2023, lifting off on a Falcon Heavy rocket from Kennedy Space Center in Florida. The launch did the hardest part in one push. It gave the spacecraft enough energy to escape Earth's gravity well and place it on a heliocentric orbit around the Sun. Once the upper stage released the spacecraft, the work passed from chemical rockets to something much gentler but far more patient: solar electric propulsion. From that moment on, Psyche has been, in a sense, another small planet orbiting the Sun, following its own elongated path that gradually evolves toward the orbit of asteroid 16 Psyche. The mission doesn't head directly outward. Instead, it first travels through the inner solar system, looping inward and then outward in a carefully calculated pattern. Along this path, the spacecraft will meet another world, Mars. Around 2026, Psyche will perform a gravity assist flyby of Mars. In orbital mechanics, a gravity assist is not a slingshot in the cartoon sense, but a precise exchange of momentum. As Psyche sweeps behind the planet along its orbit, Mars's gravity bends the spacecraft's trajectory and changes its speed relative to the Sun, without burning additional propellant. For the mission team, that maneuver is like nudging a billiard ball at just the right angle so it will roll onto a new track that leads outward to the asteroid belt. After the Mars flyby, Psyche's orbit around the Sun becomes larger and more Psyche-like. The spacecraft spends several more years slowly climbing outward, its ion thrusters operating for thousands of hours. These thrusters accelerate charged xenon atoms, creating a faint blue exhaust that produces only a small push at any moment. But over time, that continuous push adds up. Day after day, the spacecraft gently reshapes its solar orbit, closing the gap with its namesake asteroid. Late in the decade, roughly around 2029, the two paths intersect. At that point, NASA's Psyche is no longer just traveling near its target's orbit. It must match its motion precisely. This is where the long years of electric propulsion and trajectory tuning pay off. Rather than diving past at enormous speed in a brief flyby, the spacecraft carefully adjusts its velocity so that when it arrives, it can be captured into orbit around 16 Psyche by the asteroid's own gravity. Once captured, the mission transitions from interplanetary cruise to orbital science operations. Psyche's time at the asteroid is organized into several distinct orbital phases, each at a different altitude. The spacecraft will begin in a relatively high, loose orbit. From there, the team can safely refine the gravity field model. Small variations in the spacecraft's motion reveal how mass is distributed inside the asteroid. This high vantage point also yields a first complete global shape model and basic maps of surface brightness and color. With that information in hand, the mission can carefully step down to lower orbits. In each successive phase, Psyche flies closer to the surface, improving the resolution of its images and compositional maps. Higher orbits are best for stable gravity measurements and broad surveys. Lower orbits are used to resolve smaller craters, ridges, and possible metal-rich or silicate-rich regions on the surface. Over months, the spacecraft repeatedly circles Psyche, building up a three-dimensional picture of its topography, density structure, and composition. Throughout this period, the solar electric propulsion system remains a quiet but crucial player. The large solar arrays, spreading several meters across, gather sunlight even out near the main belt, powering the ion thrusters when small orbit adjustments are needed. Electric propulsion is not just how Psyche gets to its target. It is also how the spacecraft can fine-tune its orbital paths, shift between mapping phases, and eventually, if needed, raise its orbit for mission extension or safe disposal. Taken together, Psyche's trajectory and timeline reflect a new era in deep space exploration, one where missions are designed around long, efficient cruises, assisted by planetary flybys and driven by sunlight-powered electric engines. It is a journey that turns the whole inner solar system into an intricate set of stepping stones, leading slowly but surely to a single, mysterious object, a possible fragment of a planetary core, waiting in the asteroid belt. The Psyche spacecraft is essentially a flying laboratory built to touch a possible metal world without ever landing on it. From a distance of hundreds of kilometers above 16 Psyche's surface, it has to reconstruct the asteroid's composition, internal structure, and magnetic history using only light, particles, and gravity. To do that, engineers built a bus surrounded by two enormous, cross-shaped solar arrays that span more than 20 meters tip to tip. Even in the dim sunlight out in the main belt, those arrays generate enough power to run both the science instruments and the spacecraft's solar electric propulsion system. Instead of short, powerful chemical burns, Psyche uses efficient ion thrusters. Xenon gas is ionized and accelerated by electromagnetic fields, providing a very gentle but continuous push. Over years, this steady electric thrust bends the spacecraft's orbit from Earth out into the asteroid belt, guided by periodic trajectory corrections and a gravity assist at Mars. The same power system that feeds the ion engines also sustains the instruments that will read Psyche's fossil record once the spacecraft settles into orbit. The main way Psyche will see its target is with its multispectral imager, a pair of identical cameras mounted on a pointing platform. Each camera can record high-resolution images through a set of color and near-infrared filters, turning light reflected from the surface into maps of both shape and composition. At high altitude, the imager will capture global views that reveal the asteroid's overall outline, large impact basins, and major geological units. As the orbit lowers, it will resolve individual craters, ridges, landslides, and boulders, and by comparing images taken from different angles, the team can build a detailed three-dimensional shape model. The filters act like a chemical fingerprint reader. Subtle changes in brightness at specific wavelengths tell scientists where metal-rich regions dominate, where silicate rock is more abundant, and how these materials are mixed across the surface. If Psyche is an exposed core fragment, the imager should detect broad metallic plains, possible solidified lava-like textures of once molten iron or nickel, and perhaps patches where later impacts have excavated pockets of silicate crust or mantle material. To move from surface pictures to actual chemistry, Psyche carries a gamma-ray and neutron spectrometer mounted on a boom that projects away from the spacecraft body. High-energy cosmic rays constantly bombard 16 Psyche, penetrating below the surface and triggering nuclear reactions in the upper tens of centimeters of rock and metal. The excited nuclei then emit gamma rays and neutrons with energies characteristic of specific elements. By measuring the energies and intensities of this radiation over many orbits, the GRNS instrument can derive the abundance of iron, nickel, silicon, sulfur, potassium, and other key elements in different regions of the asteroid. If large areas are dominated by iron and nickel alloys and depleted in lighter elements, that would support the exposed core hypothesis. If instead the elemental mix is more like a metal-rich stony body, it would suggest that Psyche's history involved partial differentiation or violent mixing, not a clean stripping of a fully formed core. In either case, the gamma-ray and neutron data turn the surface from a visually interesting landscape into a quantitative map of planetary-scale metallurgy. A small but crucial instrument on Psyche is the magnetometer, mounted on the same boom to keep it away from the spacecraft's own magnetic fields. It measures tiny variations in magnetic field strength and direction around the asteroid as Psyche orbits. Planetary cores that once generated a dynamo, a self-sustaining magnetic field driven by convecting liquid metal, can preserve a fossil magnetization when they cool and solidify. If 16 Psyche is a remnant of such a core, parts of its interior could still carry this ancient magnetic imprint. Detecting a coherent, remnant magnetic field would be a powerful sign that Psyche once belonged to a larger, differentiated body with an active metallic core, similar in principle to the deep interiors of Earth or Mars. Conversely, a lack of detectable magnetization might point to a different origin, such as incomplete melting or assembly from multiple smaller fragments that never experienced a strong, global field. The magnetometer thus gives access to a layer of history that no camera can see, the invisible memory of past planetary dynamos. Even the radio link that sends data home doubles as a scientific instrument. Psyche communicates with Earth using X-band and Ka-band radio waves through its high-gain antenna. By tracking the tiny Doppler shifts and timing changes in those signals as the spacecraft orbits 16 Psyche, scientists can map the asteroid's gravity field with high precision. Variations in the spacecraft's speed and path reveal how mass is distributed inside the asteroid, whether it is relatively homogeneous, whether there are dense metallic cores beneath lighter regions, or whether voids and low-density structures betray a rubble pile interior. When combined with the overall shape and volume derived from imaging, these gravity measurements yield the bulk density and help distinguish between a solid block of metal, a mixed metal or rock body, and a heavily fractured or porous object. In effect, radio science turns Psyche into a planetary-scale CT scan, showing where the weight really is inside this unusual world. Along the way to Psyche, the spacecraft also carries a pioneering technology experiment, Deep Space Optical Communications, or DSOC. This system uses a near-infrared laser to send and receive high-rate data streams between the spacecraft and a specialized ground station, demonstrating how future missions might communicate using light instead of, or in addition to, radio waves. DSOC operates only during the cruise phase and is not part of the core science payload, but it shares the same deep space environment and navigation challenges. If successful, it will pave the way for far more data-rich exploration of the outer solar system, including future missions that might orbit other metal-rich bodies or even return samples from them. Together, the solar electric propulsion, advanced imaging, nuclear spectroscopy, sensitive magnetometry, precision radio science, and optical communications make Psyche not just a visit to an unusual asteroid, but a testbed for the next era of deep space exploration. If 16 Psyche really is the exposed core of an ancient protoplanet, then it is the closest we will ever come to orbiting the heart of a rocky world. The mission is, in essence, an attempt to catch a planetary core in the open. No mantle, no crust, just metal and rock written in a different language than anything we see on Earth's surface. The instruments on Psyche are tuned to answer a simple but profound question. Is this object built like a planet on the inside? One of the first clues will come from the magnetometer. On Earth, our global magnetic field is generated by a churning, liquid iron and nickel core that acts as a dynamo. If Psyche is truly the remnant of a once molten core, it may retain a fossil magnetic field, weak, patchy, but still detectable. By carefully mapping any remnant magnetization as the spacecraft orbits, scientists can test whether Psyche once hosted a core dynamo of its own. A clear, organized magnetic signature would be a smoking gun, direct evidence that this body behaved like a miniature terrestrial planet in its youth. At the same time, the gamma-ray and neutron spectrometer will read Psyche's elemental barcode. Galactic cosmic rays constantly strike its surface, knocking loose gamma rays and neutrons whose energies depend on what elements are present. By collecting that radiation over many orbits, the instrument can infer the abundance of iron, nickel, and lighter elements such as sulfur and silicon. A composition dominated by metallic iron and nickel, with specific proportions of lighter elements, would support the idea that Psyche represents material that once segregated into a core. If instead the measurements show a more mixed, chondritic-like pattern, that would suggest a different story, one where metal and rock never fully separated. Gravity and topography provide the third line of evidence. As Psyche circles the asteroid, tiny changes in the spacecraft's speed, tracked through its radio link with Earth, reveal how mass is distributed inside. Combined with detailed shape models from imaging, this gravity field can show whether Psyche is relatively uniform or strongly layered. A dense, centrally concentrated interior would be consistent with a core-like body, while a more irregular gravity field could point to a complex, partially differentiated or heavily disrupted object. Craters, ridges, possible metal-rich outcrops, and deep basins on the surface will all help reconstruct the sequence of impacts and heating that Psyche has endured. But there is a real possibility that Psyche will turn out to be a hybrid rather than a pure core. It might be a mashup of metallic and silicate material, where differentiation started but never finished, or where later collisions shredded and reassembled the body. In that scenario, large regions of exposed metal could coexist with rocky plateaus and mixed terrains. For planetary scientists, this is not a disappointment, it is a new kind of laboratory. A partially differentiated Psyche would reveal a stage of planet formation we can only model today, when small worlds are hot and mobile enough for heavy elements to sink and light rocks to rise, but the process is interrupted by violent impacts and rapid cooling. Whatever Psyche turns out to be, it will reshape how we think about the deep interiors of rocky planets. On Earth, our core is forever hidden beneath thousands of kilometers of rock. We study it indirectly through seismic waves and global magnetic behavior, building models but never seeing the material itself. Psyche offers a rare chance to compare those theoretical expectations with a real object that may have followed a similar path, just on a smaller scale and with its interior exposed to space. If we can match Psyche's density, composition, and possible magnetic history to our models of core formation, we gain confidence in applying those models to Earth, Mars, Mercury, and rocky exoplanets we will never visit. Even if Psyche is ultimately classified as something more complicated, a disrupted fragment, a reaggregated body, or a unique mix of metal and rock, it will still answer questions we do not yet know how to ask. Its surface textures will tell us how metal behaves under billions of years of micrometeorite bombardment. Its craters will record the impact history of the asteroid belt in a material we have never mapped at this scale. And its internal structure will either confirm or challenge our assumptions about how far differentiation progresses in small worlds. In that sense, Psyche is less a destination and more a diagnostic, a single, strange object that can either validate the story we tell about planetary cores or send us back to rewrite the opening chapters. In the end, when Psyche settles into its lowest mapping orbit, every pixel in every image, every subtle tug on the spacecraft's trajectory, and every faint gamma ray will contribute to one overarching experiment. Can we read the history of planet building directly from a metal-rich body in space? If the answer is yes, Psyche will become our benchmark for what a planetary core, or something very close to it, looks like when the universe leaves it exposed. For years, headlines have claimed that Psyche contains metals worth more than all the money on Earth or quadrillions of dollars. It is an irresistible story, a single asteroid in the main belt, packed with iron and nickel, just waiting to be mined by some future spacefaring civilization. But while those numbers sound spectacular, they are mostly marketing, not science. They usually come from taking a rough estimate of Psyche's mass, assuming it is made almost entirely of iron and nickel, and then multiplying that mass by current commodity prices on Earth. This ignores almost everything that matters in the real world: the cost of reaching, extracting, processing, and transporting that material, the fact that flooding Earth's markets with that much metal would instantly destroy its price, and, most importantly, the basic truth that we do not yet know Psyche's precise composition or internal structure. From a scientific perspective, Psyche's value is of a completely different kind. Even if it turned out to be far less metallic than early models suggested, it would still be one of the only places in the solar system where we can directly study material that may have formed under core-like conditions. Its metals, silicates, and possible sulfides are not interesting because they might be melted down into steel beams or sold on a commodity exchange. They are interesting because they record pressures, temperatures, and chemical environments that shape the interiors of infant planets. The mission is designed as a geological and geophysical investigation, not a prospecting expedition. Every spectrum, gravity map, and magnetic field measurement is aimed at reconstructing how differentiation, impacts, and mixing proceeded in the earliest tens of millions of years after the Sun formed. At the same time, Psyche fits into a longer-term story about how we might one day interact with asteroids as resources. Over the past decades, we have learned that small bodies are far more diverse than simple rocks in space. Some carbon-rich asteroids contain hydrated minerals and trapped water that could, in principle, be turned into drinking water, breathable oxygen, or rocket propellant. Others, especially more metallic objects, may concentrate iron, nickel, and platinum group elements far above average crustal abundances on Earth. In a distant future where heavy industry moves off-planet, such bodies could become quarries for constructing habitats, spacecraft, and large structures in space, avoiding the need to lift every kilogram out of Earth's gravity well. To make any of that real, however, we need to understand what these bodies are like mechanically and geologically. Are they solid or rubble piles? How do their surfaces behave under drilling or anchoring? How variable are they from one object to another? In that sense, Psyche is a pathfinder. It will not be mined. It will not send back ingots or ore. Instead, it will tell us whether a metal-rich asteroid is a coherent block of iron, a jumbled mixture of metal and rock, or something in between. It will show us whether such worlds can preserve magnetic signatures from an ancient dynamo, how fractured or porous their interiors may be, and how metals and silicates are distributed on and beneath the surface. Those answers will feed directly into our models of planet formation and indirectly into any future plans for in-space resource use. The real treasure Psyche offers is knowledge, a once-in-a-solar-system chance to study, up close, a kind of object that may bridge the gap between raw building blocks and the hidden cores of full-grown planets. From the moment Psyche left Earth, the mission has been as much about patience and precision as it is about exploration. After launch on a Falcon Heavy from Cape Canaveral in October 2023, the spacecraft did not immediately head straight for the main belt. Instead, it slipped onto a carefully calculated heliocentric path, beginning a multi-year cruise phase through the inner solar system. Those first months after launch are quiet only on the outside. Inside the flight timeline, they are dense with checkouts and rehearsals. The spacecraft's systems are powered on in stages, each subsystem tested, calibrated, and cross-checked. The multispectral images take first light images of star fields and distant objects, not for science, but to verify focus, pointing stability, and detector performance. Engineers compare these early frames with ground expectations, tuning exposure times and image processing pipelines so that, years later, when Psyche fills the field of view, every pixel will count. The electric propulsion system also goes through its paces. Psyche's solar electric ion thrusters are designed to provide a gentle but continuous push over years, trading raw power for exquisite efficiency. Early in cruise, mission controllers test different throttle settings and gimbal angles, measuring how the tiny thrust translates into changes in the spacecraft's trajectory. Navigation teams feed those data back into their models, refining how they will steer Psyche through deep space with minimal propellant. At the same time, the Deep Space Optical Communications (DSOC) technology experiment begins its own test runs, sending narrow beams of laser light back toward Earth to explore the future of high-bandwidth communication across interplanetary distances. All of this activity leads toward a key milestone: the Mars Gravity Assist. In 2026, Psyche will sweep past Mars, not to study the planet but to borrow a bit of its orbital energy. As the spacecraft approaches, its trajectory is aimed not at Mars itself, but at a carefully chosen aim point behind or ahead of the planet. Mars gravity bends Psyche's path and subtly alters its speed relative to the Sun, changing the shape and tilt of its orbit without expending large amounts of xenon propellant. From Earth, the geometry can be drawn as a simple curve. In reality, it is a precisely choreographed dance in a moving three-body system: Sun, Mars, spacecraft. The flyby is also an opportunity to test Psyche's instruments on a real planetary target. Even if only a brief imaging campaign is planned, it lets the team practice rapid sequence photography, on-the-fly adjustments to exposure and pointing, and coordinated operations between cameras, spectrometers, and the spacecraft's attitude control system. It is effectively a dress rehearsal for the far more demanding conditions at the final destination. After Mars, the mission settles into its long outbound leg toward the main asteroid belt. Over the next several years, Psyche's ion thrusters pulse through planned campaigns, gradually raising the spacecraft's aphelion until it intersects the orbit of 16 Psyche itself. From the perspective of the spacecraft, the Sun slowly shrinks, solar power margins tighten, and thermal conditions change. The operations team adapts, managing power carefully between propulsion, instruments, and communications. Months before arrival, 16 Psyche transitions from a calculated point on a star chart into a faint, moving dot in the spacecraft's cameras. This starts the approach navigation phase. Optical navigation images are taken regularly. The asteroid's tiny speck is measured against background stars, and those measurements refine the orbit solution. Radar-derived shape models from Earth-based observatories are combined with the new optical data to predict how Psyche's apparent size and phase will evolve as the spacecraft closes in. Trajectory correction maneuvers are planned and executed with increasing precision. As distance shrinks, that point of light blooms into a resolved disk. Subtle albedo variations appear first, then limb topography, then recognizable craters, slopes, and bright and dark patches. For planetary scientists who have spent decades working only with indirect data, radar echoes, spectral curves, density estimates, these first detailed images are transformative. Features that were once abstract parameters in a model become cliffs, basins, ridges, and possibly metallic outcrops on a real landscape. The mission shifts in tone, from going to Psyche to we are now at Psyche. By the time the spacecraft slips into its initial high science orbit, the team already has a global view of the asteroid's shape and rotation. Each subsequent lowering of the orbit will sharpen that picture and tie morphology to gravity, composition, and, perhaps, relic magnetism. But the emotional turning point is that first sequence of close images, the moment when a long-theorized metal world stops being an idea and becomes a mapped, measured, and named place in our solar system. Psyche is more than a strange object in the main asteroid belt. It is a test of our entire story about how rocky planets are built. For decades, planetary science has relied on indirect evidence to understand cause. Seismic waves on Earth, density estimates for Mars and Mercury, models of how molten metal separates from rock in a young, heated world. But all of those inferences are based on worlds whose hearts are buried thousands of kilometers below their surfaces. If 16 Psyche is truly rich in metal and shaped by the same processes that formed planetary cores, then this mission is our first chance to see, in the open, what usually hides at the very center of a planet. By orbiting Psyche, we are effectively performing a core biopsy on a world that never finished becoming a planet. The spacecraft will map its gravity field to reveal how mass is distributed inside. It will measure elemental abundances with gamma rays and neutrons, searching for the fingerprints of an iron and nickel body with lighter elements mixed in, as we expect in terrestrial planetary cores. Its magnetometer will listen for the faint echo of an ancient magnetic field, the kind that can only be generated by a once liquid, convecting metallic interior. If those signals align, we will have our strongest evidence yet that catastrophic collisions in the early solar system could strip a young world down to its metallic heart and leave it drifting, alone, between Mars and Jupiter. And even if Psyche defies that expectation, the mission will not have failed. If it turns out to be a more complex hybrid of metal and silicate, or a partially differentiated body frozen halfway through its evolution, that will be just as important. It would tell us that the early history of rocky worlds was not a simple sequence of melt, separate, form a neat core, but a messy spectrum of outcomes, worlds that were shattered and reassembled, interiors that only partially divided into layers, fragments that record states of matter and structure we have never seen before. Whatever Psyche is, its true nature will force us to refine how we think planets grow, break, and rebuild. For Earth, this matters deeply. Our own core governs the planet's magnetic field, shields the atmosphere from charged particles, and affects the long-term evolution of the mantle above it. Yet we can never drill to it, never see it directly. Psyche offers a rare external mirror, a body that may have experienced similar early processes, but with its interior exposed to our instruments. By comparing what we see at Psyche with what we infer about Earth, Mars, and Mercury, we tighten the link between theory and reality. In a sense, by traveling hundreds of millions of kilometers outward, we are also looking inward, toward the inaccessible center of our own world. If Psyche is truly the exposed heart of a failed world, then this mission is not just a flyby of a rock. It is a visit to a planet that almost was, a body that never had oceans or a sky, never cooled into continents or weather, but still carries in its metal the memory of how such worlds begin. If it is instead a tangled mixture of metal and stone, it becomes the fossil of a different kind of history, a record of violence, reassembly, and unfinished differentiation that shows just how chaotic planet formation can be. In both cases, Psyche is a fragment of a larger story written in collisions, molten interiors, and shattered crusts. When the first close-up images arrive, 16 Psyche will stop being a distant, unresolved point and become a real place, scarred slopes of metal-rich terrain, impact basins and materials we have never touched before, textures that hint at molten pasts and broken futures. From then on, every time we talk about planetary cores, giant impacts, or the early sculpting of the solar system, Psyche will be in the background, not as a number in a model, but as a world we have actually seen. After this mission, it will be harder than ever to dismiss asteroids as cosmic debris. Each one, and especially this one, is a surviving piece of the machinery that built the planets. Psyche reminds us that worlds do not simply appear. They are forged, broken, and sometimes left unfinished, their hearts still exposed to the dark.